previous video, we were looking at the duality of sorting and hashing. We talked about sorting, how sorting changes based on the scale of the data. So let's look at hashing now, and then we compare the two techniques with a practical example. Hashing corresponds to the fact that you would look at the data set by effectively picking up some columns or a set of columns and computing a function on top of it, which allows you to quickly identify whether that combination of those values in those columns are unique. So the example here is, let's say one of your columns is related to an ID. ID could be a customer ID, could be a PAN number, mobile number, email address, whatever it is, and you wanted to quickly know whether that particular ID has been encountered before in the data set, or you want to quickly know whether you've seen that specific email address earlier, in which case, instead of searching all over the data again, you could simply use a hash function as a unit of computation, such that you could index, rather you could look up a specific table and count the occurrence of that specific value of that key, right, value of that ID. So the way to understand this is a hash function is a one-way function mathematically, which takes a bigger domain of data, right, and then produces a smaller range, such that the execution of that function is super fast, right? So it's optimized for ensuring that you don't have to individually compare the byte by byte of data values, but instead you could compute a smaller ranged value, which you can then use for comparison, and that makes it faster, that makes it better. So from a scalability perspective, when you have to start looking at occurrences of values like IDs, for instance, at very large scale, and then look at repeat occurrences, then you could use a hash function to compute the smaller ranged value of that same ID, and then index that smaller ranged value into a memory-based structure, which is called as the hash table. That way, you get access to comparisons of data elements very quickly, and you get access to a data structure which allows you to do other operations on top, like counting, like flagging occurrences of using a Boolean variable, etc., etc. So here, the fundamental assumption made is, in order for you to index a unique value of data, you need to have enough memory, right? In that, you need to have enough availability of memory in order to create that hash table, right? So that's where there is a distinction between a hash table which is large in size versus a hash table small in size. For small scale data, the hash table itself can fit in memory, so you can just treat it as one single hash table and then do your hash algorithms on top of it. But the moment the data becomes large in scale, but here what I really mean is not volume of data, but the size of the range of the hash function, which means the uniqueness of the keys that you're indexing, that you're using to compute the hash on. If those are large in size, right, if the range is large, if the domain is large, such that the sum total of all the values which are possible in the domain doesn't fit in memory, right, then the hash table cannot be constructed in a single shot in memory. You will have to think about what's called as a partitioned hash table structure, and we can talk about that with more examples at a later point in time. But notice that the ability to deal with scale for a hash algorithm, for a hash-based computation, is very different for the versus the sort-based comparisons, right? So in a sort-based structure, the amount of memory that you have available dictates the size of the amount of data that you have that you can read at any point in time to sort. Whereas in the case of hash algorithms, it's not the size of the data that matters, it's the size of the domain of the keys that you're actually using to hash on or to index on. So that matters more. So let's take a look at with a practical example of a problem statement of counting, right? And I'm going to count the total occurrences of events of a certain kind. Let me try to get the mouse pointer here. Yeah. So the input data set for me is what's called as a clickstream, right? A clickstream is basically a user clicking on a specific URL at a particular point in time on this date. So for simplicity, I've just removed all the other columns which are not necessary. But I've retained the user ID column, the time and the date. I want to be able to count the number of clicks that a user made in a time interval, and I want to group time intervals based on 6-hour blocks. And because these are 6-hour blocks, there will be 4 such blocks, right? 1 to 6, which is basically 1 AM to 6 AM, both hours included, 6 AM to 12 AM, 12 AM, rather 6 AM to 12 PM, 12 PM to 18 PM, which is 6 o'clock in the evening, and 18 to 24, right? And for each block of 6 hours, I want to count the number of users and the clicks that are being made, right? So with this data set as input, I want to be able to say between 1 to 6, there were 4 clicks, between 6 to 12, 8 clicks, etc., etc. So how do we go from this data to this answer? There are 2 mechanisms of doing this. One involves sorting, the other involves hashing, and this demonstrates the duality very easily, right? Very easy for you to understand. So to get to the answer that we want, first and foremost, let's assume that this data set is very large in size. Now, the reason it makes sense to make that assumption is because, firstly, we're in a course of big data, so we want to make that assumption, we want to know techniques associated with that. But secondly, it's easy for me to explain parallelism, right? The moment we make this assumption and then start to assume that we have to execute in smaller chunks of data in parallel, right? So let's make that a simplifying assumption, which means I need to be able to break the data into chunks. So for the purposes of this example, I've broken this data into 5 chunks, and these 5 chunks are like uniform, right? So I don't care how the chunks are made. The chunks could have different IDs, and doesn't matter to me. I'm just going to break it down uniformly, like picking the first 6 rows of data together, next 6 or 7 rows, 6, 7 or 8 rows, etc., etc., right? So I'm just clubbing it all together into contiguous rows. Now, each chunk by itself does not have any specific pattern, right? It's just a bunch of data randomly picked up. Within a chunk, I start to do some operations. Using sorting as the foundational algorithm, a foundational operation, one of the first things that I do is I sort the data within a chunk. So in this first case, remember that the problem statement I'm trying to solve for is grouping data into counts based on hour of the day. So hour of the day, of course, time of the day matters as well. So what I do is I sort the data based on ascending order of time within a chunk. So in this chunk, 6 comes first, 809, 945, etc., etc. Right? Likewise, the next chunk has its own sorting. The next chunk has its own sorting, etc. But notice that across chunks, the data is not sorted, right? I still have occurrences across chunks which are interleaved, right? Not necessarily sorted. Once I sort the data across chunks, then I can start to do a count of what I really need. Because the data is sorted across chunks, I know for a fact that the time block that I'm interested in will occur continuously, and once it stops occurring, it will not occur again. What I mean by that is the time element 1 to 6, right, will occur first because it's sorted by time. Once the last of the rows which contributes to this time block is done processing, and I've encountered the next time block, which is 8 o'clock, right, onwards, I know for a fact that I will never get another time instance in that chunk which corresponds to the 1 to 6 block. Therefore, the count that I need to maintain in memory, right, is only going to be the 1 to 6 aggregate at any point in time, right? Once 1 to 6 is done, I can emit out that as the answer for that block for my chunk and move on to the next time block. So with this kind of a technique, I'll be able to emit out answers as and when a particular time block is done, right? 1 to 6 is done or 6 to 12 is done, etc. for each chunk in parallel, and that way I can limit the use of memory here to, for the final count, I can limit it to at any point in time only one block of time that I'm currently computing, one block of 6 hours that I'm currently computing. But for other memory usage, I'll have to worry about how do I do the sorting. So here I made the simplifying assumption, each chunk can fit in memory. So I need as much memory as is required for doing a quick sort on this chunk, and I need one extra one extra unit of memory for each time block here. So as and when a chunk is done completely, I'll have these answers, right, for each time block, and each time block will be also present in potentially all the other machines as well, all the other chunks as well, right? So once I'm done with all the chunks, then I can do a shuffle operation, and as part of the shuffle operation, I bring the time blocks together. When I bring it together, I'll then get each chunk's contribution for that specific time block into the same task of operation, and then within that task of operation, I'll have a bunch of these counts corresponding to each chunk, and on top of it I can do the sum of those counts. So the same thing will happen for the other time blocks, because they will all get brought together by the shuffle operation. So notice that for that to happen, the shuffle operation had to be shuffling based on the value of the time block, right? And then once the final once the final operation on each time block is done, which is a sum of partial counts, then I have the final answer. So in this way of solving for counting, we leveraged multiple different techniques that we've already seen. First and foremost is divide and conquer. We took up the broader problem statement of the big data that we assumed is large in size, right? Broke it down into smaller chunks which we executed in parallel, shuffled across to create the final input data for the final operation, which then created the final outcome that we needed, which we then coalesced, right, collected together to create the final outcome. So that's divide and conquer, classic, right? Second thing that we also did here was use sorting locally within a chunk as a means of solving for one step in this problem statement. Once the sorting was done, we noticed that we could just at any point in time keep in memory only the counter corresponding to the current sorted data that was being explored, right? And that we knew based on the fact that we wanted time blocks as the final output, final unit of output. So we could use that assumption. We could use that part of the problem statement to only store that counter at any point in time when each chunk is getting processed. And then finally, we also took a look at how we leverage this breakdown of the aggregate of sum, or rather the count aggregate, into count that happens on embarrassingly parallel fashion, followed by the sum of partial counts, right? So we leverage that as well. Let's look at the hashing based approach for solving the same problem. So before we do that, what would you say is the time complexity of this type of an algorithm? First and foremost, the task of splitting the larger data into chunks is cheap. I can just simply decide to cut off the chunk processing based on the row count, right? Assuming the row count is available as a statically computed value when the data was first created, so the chunk creation can be done in constant time, I don't need too much time for it. Definitely not in the order of magnitude of the data itself, right? Next up, for sorting data, I can do a sort locally within a chunk. So I could use quicksort for it. That's big O notation n log n, but that's happening in parallel across all the chunks, assuming there's enough executors available for it. So that's big O notation n log n. Then the computation of the count for each block of window is straightforward, right? It's constant time because I just have 4 blocks of window. It doesn't matter the size of the data, so I don't need to spend too much time for this. It's constant time. And then once I have the final answers for each chunk, which are representing the partial counts, then I do a shuffle operation. The shuffle operation transfers over the network in the worst case, but because the data being shuffled here is only the partial counts per block of hours, at the maximum I have 4 such blocks and 4 such counter values, right? So again, it's constant in terms of value, rather constant in terms of size of the data, definitely not order of magnitude of the input data set, right? And then that shuffle finishes, and then the final count is also constant because the number of tasks are constant, right? The number of tasks are 5, that produces 5 rows of time blocks of data for each block of data. It's constant sized in terms of output. So net, the order of complexity of this kind of an operation corresponds to the quicksort algorithm, right? Which is order n log n. Let's look at hashing now. In hashing, remember we said that we want to be able to look at ways in which we can make comparison operations as equal, comparison operations as lookup operations using a hash function. So what's a good way to define this hash function? Because I know the final answer that I want is based on time block of window, I could create a hash function which looks at the time of day and computes which hour, which block of hours it corresponds to, right? So imagine writing a Python program which just takes the time of day and then maps it to the closest hour block, and that kind of a function that that can execute in Python is a constant time function because it just looks at one row and it takes extremely small amount of time for that function to execute. So if I have access to that kind of a hash function, then for each chunk of data that I have access, that I need to process, I can execute the hash function and automatically index it to a specific value in the hash table. And when I index it, I can pick up that memory location that corresponds to that block of window, look at the counter that exists at that particular point in time, and then increment it by 1 for that row that I'm processing at that particular point in time. So which means I will still get the output as, for that chunk, what is the count per block of 6 hours, but at any point in time I'll need to store all of the blocks of 6 hours in memory, because at any point in time while reading the chunk of data, I could read any row which corresponds to any of the 4 6-hour blocks of window, 6-hour blocks, right? Because I'm reading the data at random. So in essence, the hash computation function is constant time, is big O notation 1, which is constant time, and the counter update is also a constant time function, and I'll also need to be able to store 4 blocks of 6 hours each in memory, which is also constant in terms of memory utilization. So the only cost associated here of this function will be the cost of reading the data, which is big O notation n, right? So I'll need to read all of the data once at least, right, in order to do this operation. Notice that I'll need to do the same thing even for sorting, right? In order to do quicksort, I'll need to do I'll have to read all of the data at least once, but in big O notation, all of the data reading once is n, but the sorting operation takes n log n. So the simplification here is in big O notation, it's just represented as n log n because n is smaller than n log n. But whereas in the hashing function, there is no other complex function, no other complex operation. The only operation is just reading the data, so which is basically order n. So with order n and constant memory, I'll be able to get the partial counts as before, as done with the sorting based method. Now once I have the partial counts, again do a shuffle, get the final set of blocks of data together with the partial counts, do a sum on top of it, I get the answer. So the distinction between the hashing way of doing it and the sorting way of doing that is that in the hashing way of solving this problem, I'm able to get the answer slightly faster for this example. In return, what I've traded off is more memory at any point in time in terms of usage, right? Now, in the case of sorting, I also trade off more memory, by the way, right? Because the quick sort operates on n log n, and n here corresponds to the size of the chunk of data, which is 6 rows here. But the advantage I have with sorting is that if I don't have enough memory to process this chunk of data, I could use merge sort and process smaller chunks of data at any point in time, so that my total memory footprint is minimized. Right? That's available in a sorting based method. In a hashing based method, the hash table has to fit in memory. Otherwise, you have to use partition hash tables, which makes it slightly more complex in order to implement, which makes the hash function evaluation more complex. Right? It's just not as simple as taking a time of the event and mapping it to the block of 6 hours. So in that kind of a setup, the memory utilization for hashing is more, and therefore I've traded off memory in order to actually optimize for speed. Yeah, with that we've concluded the foundations of big data. So what we have covered is why big data was necessary with respect to how small data was reading, was accessing, solving data problems, and how it was failing when it came to data sets of very large volume or very high on complexity or very high on velocity. And then we look at how the advent of big data did not change the motivation for why data science, right, or why data engineering needed to be done. What it changed was the tooling, right? And in order to understand the tooling more, we had to look at what is the foundational design pattern of such tooling, and that was divide and conquer. We looked at examples of divide and conquer. We looked at how even a simple problem like doing a count changes dramatically, right, when it comes to big data. You have to think in terms of solving the problem with partial counts and then finally summing up the partial counts. And that was just one example, right? If you had more examples of more complexity, like for instance predicting fraud, right, or predicting outcomes, then you have to really think in terms of divide and conquer carefully, and then potentially chain a bunch of these divide and conquer steps, not just have one divide and conquer step, but chain a multiple of those. So those were like potentially more complex. But the good news is that with processing frameworks like MapReduce and Spark, a lot of this complexity is hidden for you. You could just directly use the pre-built implementations that are available with these libraries. But then, in order to use these libraries, you really have to understand what are those libraries designed for and what are they optimizing for. In the case of MapReduce, because it was the first divide and conquer algorithm for big data, not algorithm, divide and conquer programming framework for big data, it was optimizing for making sure that you made progress even in the face of very large data sets and failures on the clusters on which it was operating. But over a period of time, as more expectations were put on top of big data tooling, especially on speed and on being able to support variety of different types of workloads, Spark evolved as an open source project, and Spark evolved to basically say that, look, speed is more important, at times more important than optimizing for memory or optimizing for being able to pick up from where the failures were resulting in lost outcome. So in that case, Spark actually decided that memory was more important, rather speed was more important in lieu of memory. So it fundamentally used a planning methodology that constructed intermediate data sets which were stored in memory, such that subsequent steps can just directly read from that memory and then and then get the outputs that are necessary. And then finally, what we saw was that as algorithm designers, it's important to understand that hashing is a very useful technique to solve for very large data sets, processing them, compared to like a standard approach of sorting the data to get data in a certain predictable form. In specific circumstances, sorting is definitely better, especially when you look at the usage of memory for very large key-based storage patterns or key-based processing patterns, because hashing fundamentally depends upon being able to index a unique key with a unique area of memory, right? So in those kinds of setups for very large keys, very large domains in which the keys are distributed, the hash table could be very large in size and therefore eat up too much memory. So in those kinds of setups, sorting is better, but for the most part, hashing is a very good approach to solve for a specific problem. And in most cases, if you're able to think about a sorting-based methodology for solving a particular problem, you could definitely think about a hashing-based methodology as well, because the two approaches are equivalent for data processing purposes. Great. So with that, we have come to the end of lecture 1. So we will take you now to the assignments of getting set up. How do you get familiar with big data processing on the cloud with an example, and then you would potentially pick up one of these sorting or hashing based approaches that we saw on these 2 slides and implement them. Thank you.